Good day, students. In this clip, we're going to be going over some examples on limits involving infinity. This is part one of a three-part series. In the second part, we'll be going over limits that involve infinite discontinuities. And then on the last part, we'll talk about end behavior models, and limits involving infinity too. Okay, so let's go ahead and take a look at some foundational ideas that can help us to solve problems involving finding limits as x goes to infinity. The first thing I'm going to look at is the arithmetic of infinity. So let's write this down. Arithmetic of infinity. Whenever we're solving problems involving limits, infinite limits, it always gets reduced to some kind of operation involving infinity. And if we know how to carry out these calculations, we'll have no complications finding the answer. All right, so the first part of this is finding the sums. So let's write this down, sums. So these are the following facts you have to keep in mind when adding numbers involving infinity. So infinity, the first one is infinity plus infinity equals infinity. Okay, if you add two infinitely large numbers, you end up with one infinitely large number. Number two is n plus infinity equals the same thing as infinity plus n, and that equals infinity. All right? And note, anytime I use n, let me just put the remark on the side. N is a set of all positive reals, okay? N is a set of positive reals. Okay? All right. Now let's take a look at the next one. We have the difference. Okay? Difference. Now what does that look like? Well, for the difference, the first one, infinity minus infinity is undefined. Okay? You can't determine what infinity minus infinity is. Number two, a positive real number minus infinity is equal to negative infinity. All right? Because this number is so big, this negative infinity is so big that if you this a negative big number is so huge that if you add a positive integer to it, it has no change on this infinitely large negative number. All right? And if we do if we commute this, we're gonna have infinity minus n. This is equal to infinity. All right, notice we know that subtraction doesn't commute like addition does. So infinity minus a small positive number, relatively speaking, is infinity because this number has no impact on this tremendously large number here. Okay, number four, if we have n, which is a positive real number, minus a number that's infinitely close to that positive real number from the left, this is equal to an infinitely small negative number known as 0 to the negative. Okay, and this is the same thing as negative 1 over infinity. We'll talk more about this later. All right, and what if we have a real number that's really, really close to a positive number from the right, and you subtract a positive number from that number that's really, really close to that positive number from the right? Well, what you have is an infinitely small positive number, really, really close to 0 from the right, and that can also be written as 1 over infinity. Okay? All right. All right, so the next set of arithmetic rules I'd like to take a look at is product, okay? Product of numbers involving infinity. So, number one, what if we multiply infinity times infinity? Well, infinity times infinity is infinity squared, which is just basically infinity, all right? And then a number times infinity is equal to infinity times the number, and that's equal to infinity also. All right. What if we have 0 times infinity? Well, 0 times infinity is the same thing as infinity times 0, which is equal to 0. Okay? All right. Now let's talk about quotient. Dealing with quotient of uh, infinitely large numbers. So number 1, infinity over infinity. Well, this can't be really is undefined. You can't really determine what this is in an indeterminate form. Number 2, if you have infinity over a number, it's infinity, because you're dividing an infinitely large number into finite spaces. So you're going to have an infinite amount of numbers in each space, which is basically infinity. All right? And then the inverse of that, finite number divided into infinitely many spaces, you're going to break it so much that this number is going to get so small, it's going to basically be 0. All right? And also, if you have n divided by negative infinity, an infinitely big negative number, you're going to end up with 0 also. All right? Okay. What about we divide, if we divide a number by 0? Well, if you divide a number by 0, this is plus or minus infinity. So it's two numbers in one, so that's why it's basically not really defined. It depends on where you're coming from. So we have to use directionality here to address this ambiguity, okay? So for number 6, if you divide a number by a really small negative number, approaching 0 from the left, so this is going to become negative infinity. Okay, really an infinitely small negative number. Okay, well, technically it's an infinitely large negative number. And then number 7, n divided by an infinitely small positive number, that's going to give us infinity. So basically, what direction are you approaching 0 from tells you what the output is. But if you're approaching from both sides, you do not have a specific output as your answer. That's why this is undefined, because n over 0 captures two numbers in one. All right, so there you have it. Okay, let's take a look at power of limits. See if we can make some sense of that. So whatever if we're dealing with powers. Number 1, if you have infinity raised to the infinity, that's clearly infinity. Number 2, if you have infinity raised to a finite power, that's also infinity. And number 3, if you have a number raised to an infinite power, you're multiplying it infinite number of times, that's infinity also. Number 4, if you have infinity raised to the 0th power, that's 1. And then number 5, if you raise 0 to infinite power, you multiply 0 infinite number of times, you still end up with 0. Okay? And the last thing I'd like to touch on has to do with trigonometry, and basically how that behaves towards infinity. Okay, let's partition this. So for trig, the main thing I just want you to know for trig are the following two conditions. The first one is that sine of infinity is bounded between two numbers. Okay, sine infinity actually is plus or minus. The sign doesn't really matter, and that is bounded between -1 and 1. Remember, the range of your sine function is always between 1 and -1. So sine of any number, whether to infinity or negative infinity, is going to fluctuate between 1, -1, and everything in between. Okay? And also for cosine, the same conditions hold. If you go take cosine to plus or minus infinity, you're just going to be bounded between -1 and 1 with the boundaries included. Okay? So just basically keep these points in mind. All right, before we go into some examples, I just wanted to go over a shortcut or a trick that can help you evaluate limits involving infinity for rationals. Okay, so let's go ahead and write down what the shortcut is, and we're going to be applying it to some examples. Okay, so let P over Q be a rational expression. Okay, so P over Q is a rational expression where P and Q are polynomials. Okay, with P and Q as polynomials, and let's just declare a variable here. Let LT be the shortcut for leading term. Okay, the leading term of a polynomial is the term with the highest degree in the polynomial expression. So let's call that LT. Okay, just to save space. All right, so now there are three cases you want to keep in mind. Okay, the first one is top heavy. Top heavy is the case you have when the numerator has a greater degree than the denominator. Basically, the power of the leading term on top is bigger than the power of the leading term on the bottom. Okay, it doesn't matter the order is written. Whichever term has the biggest degree is the leading term. Okay, so top heavy, if the degree of the numerator p is greater than the degree of the denominator q, right? We have a top-heavy situation. Then in that case, the limit as x approaches infinity, actually it's plus or minus infinity. The direction doesn't really matter. The limit as x approaches, well, let's do infinity first. The limit as x approaches infinity of p over q is equal to infinity. Okay, if it's negative, then it's gonna go to negative infinity also. So we'll probably just put it in there. And also the limit as x approaches negative infinity of p over q is gonna go to negative infinity. All right, so there you have it. All right, and also in some cases when x is going to infinity, the limit can also go to negative infinity. So regardless of direction, you can either have plus or minus infinity. So if you're going to infinity, it could be plus or minus infinity. If you're going to negative infinity, it could be plus or minus infinity. So it really depends on what the problem looks like. So you just know, you just have the mind that when you have a top-heavy rational expression, it's going to be plus or minus infinity. So this shortcut doesn't tell you exactly what the answer is going to be, but it gives you an idea of what it could possibly be. So it's either going to be infinity or plus negative infinity or infinity. So I'll show you how to work out the problem, but you're going to end up with one of these two answers, okay? All right, the next situation is equal weights. Equal weights. So what does equal weights mean? Well, equal weights basically means that the degree of the numerator and the denominator polynomial expressions are equal. So if the degree of the numerator p is equal to the degree of the denominator q, then the limit as x approaches plus or minus infinity in this case of p over q is going to be the quotient of the leading terms. Okay, so all you simply do is you take the leading term of the numerator, L of t of p, and divide it by the leading term of the denominator, L of t of q. And what you find out is that since the degrees are the same, the variables will cancel out, and you're just going to be left with the coefficients. That's what you're going to be left with. But you have to do this division first in order to make sure that you have everything resolved accurately. Okay, so just divide the leading terms, because for the numerator, this is the quickest growing one, and then for the denominator, this is the quickest one. And at infinity or negative infinity, those are the only ones that really matter. Okay, and then the last one is bottom heavy. bottom heavy. Now, what's the solution? This one is nice because you know exactly what the result is going to be. There isn't any ambiguity here regarding the answer. Okay, so if the degree of the numerator is less than the degree of the denominator, you have a bottom heavy situation, then the limit as x approaches plus or minus infinity of P over Q is simply going to be 0. So 0 has no orientation, the answer is just 0. Okay? So these are some shortcuts that you can use only for rational expressions, though, that can give you an idea of what the answer is before ever you even start. Alright? So let's keep this in mind as we work on the following examples. So let's go ahead and take a look at some examples. Alright, so let's write this down. Examples. So the task is to determine the following limits, infinite limits. So determine the following limits. All right, first one, question number 1. What if we're asked to find a limit as x approaches infinity of 3x to the third minus 2x divided by 2x minus 5x to the fourth? Now, the first thing you want to ask yourself is, what kind of expression is this? This is clearly a rational expression because you have a polynomial on top and a polynomial on the bottom. So these tricks I just showed you is applicable. They are applicable here. Okay? So let's take a look at it. Is this top heavy, bottom heavy, or equal weight? All we do is focus our attention only on the leading terms. In the numerator, this is the leading term because it has the highest degree. And in the denominator, this is the leading term. You have to take the sign also because it has the highest degree. At infinity, those are the only rates that actually count, okay? So this case is top heavy. I'm sorry, it's bottom heavy because the power of the denominator is bigger. So since it's bottom heavy, this whole thing is going to collapse to 0, okay? So we already know that the answer is going to be 0 based on the fact that it's bottom heavy. But we have to show, let's show our work, okay? So let's show the work. So this becomes the limit as x approaches infinity of the leading term in the numerator over the leading term in the denominator, like that. And then we divide that out. We're going to have the limit as x approaches infinity of 3 over 5x. You subtract the small exponent from the bigger one, which is just 1. And then we'll plug in infinity into the expression. So we're going to have 3 over negative 5 times infinity. So now we're going to use the arithmetic of infinity here. Remember, when you multiply a number by infinity, you just end up with, it's going to end up with negative infinity. Now what's 3 divided by an infinitely large negative number? Remember we talked about this before on the quotient. If you divide a finite number by positive or negative infinity, your answer is always going to collapse to 0. Alright, so there goes your answer, and that's what we thought earlier, right? Because it's bottom heavy, the whole thing collapses to 0. Alright, let's take a look at another example. Question 2. The limit is x approaches negative infinity of 2x to the fourth minus 3x to the third minus 5 divided by the square root. I need to look at this. The square root of 3x to the 8th plus 5x minus 2. Okay, so what's this? Well, let's use we can use the weight situation here, but it's not really directly clear how it's applicable. Because you have the square root of a polynomial here. So if we wanted to just focus on the leading term of the denominator and the numerator, this will be the leading term of the numerator, right? So if we just wanted to focus only on that, and then if we wanted to focus on this is the leading term, we have to take it together with the square root, okay? So if you take the square root of 3x to the 8th, what is this power going to become? You divide this power by 2, so it's going to become 4. So in essence, this is going to be a fourth degree term, and this is going to be a fourth degree term. So in this case, we have equal weights. All right, so what we just have to do is divide these two, and the answer is going to be 2/3. Okay, that's what the answer is going to be, 2/3. All right, let's go ahead and show our work here. So this is going to become, so now it's going to become, well, to do it arithmetically, analytically to show our result, we're going to take the limit as x approaches negative infinity. The only thing that counts on the top is 2x to the fourth, and then the only thing that counts on the bottom is the square root of the leading coefficient, which is the square root of 3x to the 8. Everything else doesn't really count because they're going too slowly at infinity, okay? So we're going to have the limit as x approaches negative infinity of 2x to the fourth over x to the fourth root 3. Okay? You take the square root of these two, you take the square root of 3 and the square root of x to the 8th, you're going to have x to the fourth root 3. Alright, so what happens here, you see these two equal weights. These ones divide out. Alright, so your answer is going to be 2 over square root of 3. Oh, I messed up earlier. It's 2 over square root of 3, not just 2 over 3. So 2 over the square root of 3. So let's rationalize the denominator. You multiply by root 3 top and bottom. Root 3, root 3. So you're going to have 2 root 3 over 3. Okay? So there goes your limit. Okay, let's move on to another example. Number 3. What if we have the limit as x approaches infinity of 3 plus 2 minus x to the third over x to the third plus 1 times 3 over x squared plus x minus 5. What if we had this situation? How do we find the limit as x approaches infinity? That's the question. So let's take a look at this. Well, this one involves a little bit more work. We have a number, and then we have a rational expression, and a number. So we wanted to do this mentally. If you look at this piece right here, this one is equal weights, right? This one is going to be equal weights. So let me call this scratch. I'm going to do this on the side right here. This is scratch. If you wanted to do this mentally, this is how you do it, okay? So these two are equal weights. So this limit is this value is independent of infinity. So it's going to be 3. With the equal weights here, you just divide them. It's going to be minus 1, okay? And then on this area right here, you can clearly see that the degree of the numerator is 0 and the degree of the denominator is 2. It's bottom heavy, so this entire limit is going to be 0, okay? 0 minus 5, so your answer is going to be 2 times negative 5, which is negative 10. So if you wanted to do it mentally, that's how you do it, using weights, okay? Equal weights, bottom heavy. All right, let's go ahead and do the steps using arithmetic of infinity, okay? So we want to evaluate each limit independently. This limit right here, this is going to become 3 plus the limit as x approaches infinity of the leading term on the top of this, in this polynomial, in this expression, is going to be negative x to the third over x to the third. Okay, this entire thing multiplied by the limit as x approaches infinity. This term on the top is the only term that there is, so it's the default leading term, and the denominator x squared has the biggest degree, minus 5. Notice that the constants don't have limits associated with them because their behavior is independent of the direction of x. Okay, they're always that constant value. All right, so now we're going to have 3 plus. Now these divide out, right? So it's going to be the limit as x approaches infinity of negative 1. And then here, we're going to have 3 over infinity squared minus 5. This equals 3. Now negative 1 is a constant, is independent of the direction of x, so it's going to still remain negative 1, times 3 over infinity. Remember, when you divide a number by infinity, you're going to collapse to 0, minus 5. Okay? And then we have 3 minus 1 is 2. 2 times negative 5 is negative 10. So there goes your limit. All right? Okay, now how about we shift gears and do some trig types of limits involving infinity. Okay, put some trig here. All right, so what if we have the limit as x approaches infinity of sine x over x? So we're going to have to use the Sounders Theorem here. So how do we do this? Remember the initial condition I told you, right? I stated the last case for the arithmetic involving infinity. We know that sine of infinity is bounded between -1 and 1, right? We talked about that earlier, that sine of infinity is bounded between -1 and 1. All right, so let's take a look at this situation. Sine of x. If we have sine of x, we know sine of x is bounded between -1 and 1, right? So what we're gonna do, what about we divide everything by x? Divide the entire expression by x. Okay. Now, if we take the limit as x approaches infinity of these two terms, what are we going to get? The limit as x approaches infinity of -1 over x. This is bottom heavy, right? So we know it's going to collapse. It's going to become -1 over infinity, which is just 0. And also the limit as x approaches infinity of +1 over x. This is also bottom heavy, so when it's going to be 0. But let's just do the work. 1 over infinity is 0. So these two limits are 0, right? So what does that tell us? Well, let's apply it here. So the limit as x approaches infinity of -1 over x is less than or equal to the limit as x approaches infinity of sine x over x, and is less than or equal to the limit as x approaches infinity of 1 over x. So we know that these two limits are 0, right? So we have 0 is less than or equal to this limit as x approaches infinity of sine x over x, and then that's less than or equal to, this is also 0. So from the sandwich theorem, we know that if a number is sandwiched between the same number, that number has to be the value of that number, okay? So this automatically tells us from the sandwich theorem, that the limit as x approaches infinity of sine x over x is equal to 0. Okay? All right, let's try another example. Number 5. What is the limit as x approaches infinity of 1 minus cosine x over x squared? Okay, this involves a trig function, so we're going to have to make use of the Sandwich theorem one way or the other. So what about we multiply the numerator by the conjugate of 1 minus cosine x so that we can use the Pythagorean identity. Okay, so if I multiply the numerator by 1 plus cosine x and the denominator by 1 plus cosine x, what do we have? On the numerator, since we have the sum of a difference of two terms, we can use the reverse of the difference of squares factorization formula to express this as 1 square minus cosine square x. Okay? All right, and then in the denominator, we'll have this is divided by x squared times 1 plus cosine x. Okay, so using the identity here is the Pythagorean identity, which is basically tells us that, well, let's simplify this a little bit first. Well, let me write down the identity. The identity says that sine square x is equal to 1 minus cosine square x, right? That's basically what this numerator is. So let's simplify this a little bit more first, and then we'll apply that, okay? So this becomes the limit as x approaches infinity of 1 minus cosine square x over x squared times 1 plus cosine x. Okay? Now let's apply the identity. The numerator is going to change. Limit as x approaches infinity of sine square x over x squared times 1 plus cosine x. Okay, all right, let's rewrite this in such a way that we can make use of the conclusion we arrived at using the Sounders Theorem number 4. So what I'm going to do is I'm going to express this limit as follows. Express it as a limit as x approaches infinity of sine x over x times sine x over x times 1 over 1 plus cosine x. Okay? All right, so what is this limit going to be? Well, we know that this is going to become the limit as x approaches infinity of sine x over x times the limit as x approaches infinity of sine x over x. And then the last one, the limit as x approaches infinity of 1 over 1 plus cosine x. This one is hard to determine because cosine assumes multiple intervals as you approach infinity. But check this out. These two limits, we know what they are. Using the Sounders theorem, these two are 0. So this is basically 0 times the limit as x approaches infinity of 1 over 1 plus cosine x. And we know that this is automatically going to become 0. All right, so there you have it. All right, let's try one last example, and that will be that, number 6. Actually, I think this is where yeah, number 6. Okay, so number 6, let's find this another trig one, limit as x approaches infinity of x sine x plus 3 sine x, that whole thing divided by 3x squared. Okay, so it's kind of confusing, but can we rewrite this in a way where we can make use of the Sounders theorem for trig functions is the question. Absolutely, we can do that. So let's rewrite this as, what if we factored out sine x in the numerator, right? So we have limit as x approaches infinity of sine x times x plus 3, and then we separate, we put an x here, and then put the other 3x with the other term right there, 3x like that. Okay, so you can use the Sounders theorem to conclude that this limit is going to be 0. So we're going to have 0 times the limit as x approaches infinity of this expression, x plus 3 over 3x. Okay, this is going to be a equal weight situation. This limit is going to be 1/3, but does it really matter though what this limit is? Well, not exactly, because we have 0 here, and then we'll multiply 0 by this number, any number, we're going to end up with 0, okay? So we don't have to bother doing it, but if you have energy, you can write this as 0 times 1/3. But the final answer is going to be 0, okay? So there you have it. Thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel. Please post the comments to let me know what you think about this presentation, any questions, confusions, or clarifications you might have for any question or any of the properties I showed you. And you can always give it a thumbs up if you like it. And also feel free to share this on Twitter, Facebook, Google+, whatever social network you use. More calculus clips can be found on mythservice.com/calculus, or you can just scan this QR code for direct access to the website. Thanks again for watching, and have a wonderful day.